Yeah, you might have already done it. Yeah. I might have done it. Because someone said, I asked her if she said, no. She may have done
Okay, so I guess we can start. So today's lecture, I guess we're going to deliver it a bit differently, because when I was reviewing my slides for the DRAM, I didn't like them that much. I thought they are not the best way to deliver the DRAM topic. So I said I will just basically will come and we will just write while we go, right? And let's see how that goes. So the main idea is just to, again to refresh your mind about the bigger picture of what are we doing. So we spend some time. So again, this is a computer architecture course. So we are concerned about a computing system, right? All of its components. From the CPU side, we discussed few topics. It's not a very nice color. We discussed few topics like ISA, and then control and data path, which simply is answering the question of how do we implement this ISA, right? And then pipelining also. And then this bird's eye view about some other techniques like superscalar, scalar, multi-core, and this very high-level view of out-of-order scheduling, the things we discussed. We are revisiting out-of-order scheduling after we finish DRAM. And then we switch it to caches, right? This topic here. And we spend the last 2 lectures in caches. And we discussed few techniques about how we implement caches. So there is one big remaining component in computer architecture that we didn't discuss yet, which is the main memory, right? Again, at the beginning of the cache lecture, I don't know why that's not working. At the beginning of the cache lecture, we argued why memory is a bottleneck in modern computing systems, right? So we had the idea about this big gap in performance and latency between arithmetic instructions or the CPU speed and the main memory speed. And a big factor of this bottleneck is in fact coming from the main memory, from the DRAM. Good. So this is what we want to discuss now. So I hope at least some of you have already seen those DRAM DEMs. Have you ever seen a real DRAM DEM in your life, right? So DRAM is considered like a commodity product where you can go to Amazon and just basically buy a DRAM, right? Because again, if you remember from the cache lecture, we said SRAMs versus DRAMs. SRAMs are very expensive, while DRAMs are very cheap. And we said the reason for this is that DRAM technology is using a single transistor and a capacitor to store a bit, while in SRAM you need 6 transistors, right? And it's also manufactured using a different technology node, right? That's why it's too cheap. So the idea of DRAM is to trade off capacity, which is basically how many bits you can store. That's why it's in gigabytes and terabytes. Capacity and cost versus performance, access latency. Also in the caches, we mentioned that an instruction that is going for the L1 suffer a range of less than 5 cycles, while going to the DRAM, you suffer something like 100 nanoseconds, right? Like more than, well, in the range of 100 to 200 cycles of the CPU clock cycles, right? So there is an order of magnitude difference, 2 orders of magnitude difference between accessing to the DRAM and accessing to your closest cache. Good? But following the philosophy of our memory hierarchy, where you build a hierarchy of caches, everyone has its own trade-off. You make the smallest, fastest cache close to the CPU with the hope that locality will help you have a high hit rate, while you make your furthest caches, or what we call your lower levels of memory, away from the CPU, the highest capacity, because you want to store there as much memory as you can, as much data as you can, right? So this is smallest capacity but fastest, while DRAM becomes your largest capacity memory, before talking about virtual memory at the disk, but it's the slowest to access. And the overall design goal is to minimize the number of times you go to the DRAM, but then you want, when you go to the DRAM, your hit rate to be as high as you can. Like hit rate means you find your page at the DRAM, right? Because otherwise you will have to do a page swap, which is not, it's also another order of magnitude difference for access time. Good? So this is with regard to DRAM as a black box, how does it fit within our memory hierarchy and our system as a whole? So what are we going to start in this lecture? And most of this we already discussed, like this discussion that we had so far. What are we going to start, which is new to you, is, okay, what is DRAM? What is composed of? What is the internal architecture? And how do we serve requests going to the DRAM? Good? Are we good so far? Is there any question? So now if I take this DRAM block and try to draw it, so modern DRAM chips, and you realize that we have something we call DRAM, and we have something that I call here a memory control. So again, from the architecture perspective, your DRAM is an off-chip component. You see that I had this dotted line that encompasses CPU, your cache hierarchy, and your memory controller. That's basically your chip, on-chip components. while DRAMs are in fact off a chip. Off a chip means it's a different chip than your CPU chip. All of your levels of caches, again, if you remember our cache lecture, we had boxes on the chip that tells you this is an L1, this is an L2, this is an L3. So it's all within the same CPU chip, manufactured by Intel or AMD or ARM, for example. ARM doesn't manufacture, but simply whoever is using ARM chips. Good. While DRAMs are in fact manufactured completely with different vendors. Like usually you get your DRAMs. Do you know any DRAM vendor name? If you have ever bought a DRAM on your own, yeah. SK Hynix is one of the biggest. Yeah, Samsung. These two are in fact the biggest two in the market. Samsung and SK Hynix are two of the big manufacturers of DRAM. Good. So they are manufactured with different vendors and they are separate chips, right? Well, recently there are like 3D stacking of chips. So DRAM, especially high bandwidth memory, is stacked on top of the CPU chip, but that's a different topic. They are usually, we refer to them as off a chip. And part of their high access latency is because in fact they are off a chip. So you have to traverse interconnect going off a chip, which is high latency, to access your DRAM component. Good. Well, to manage accesses to the DRAM, we have an off a chip component that is called memory controller. The reason we have this, and again, I'm now discussing everything from the black box perspective, very high level, right? And then we will delve deeper into these boxes while we go through the topic. But now I have the DRAM as an off-a-chip component. Why I have a separate component called memory controller on a chip? You see that it's within my box here. Because DRAM is too cheap, you don't also invest a lot in its intelligence. So it doesn't have good scheduling capability. It's not like the caches where you have a memory controller that simply do a barrel tag access, handles cache coherence, hits versus misses. You want the DRAM to be as dumb as possible because you want it to be extremely cheap. For that reason, most of the scheduling and optimization for the DRAM is in fact done with this module that we call memory controller that is on a chip. So there is another on a chip module that handles, it's the brain of handling main memory system to handle schedule accesses, maintain DRAM state, and we'll discuss now the details of the memory controller. And in fact, your next lab is to be mainly about memory controllers and DRAM. So you will see that how memory controller components are in fact doing a lot of scheduling and reordering to optimize for memory access. Good. But all of this is done not within the DRAM chip itself. It's done on a chip with the CPU in a component we call memory controller. Good. So if you buy if you have, for example, your Intel i7 chip, it will have the memory controller on the chip itself, right? While the memory controller is outside the chip. Okay. So what are we doing in this DRAM topic is simply understand the DRAM architecture, its operation theory. There is a standard that is governing DRAM. It's called JEDEC standard. How does it work? And then how do we design an efficient memory controller again to improve performance, which is our final goal from all the topics we discuss. Good. So now delving into how DRAM is being architected or composed. In modern DRAM chips, DRAM is in fact composed of multiple banks. So it's composed of, have you ever covered DRAM banks in an electronics course? Because sometimes this is covered in an electronics course. How do you combine DRAM cells into banks? Yes? No? Yes?
Maybe a few years ago.
Okay. So it's, yeah. Okay. So anyway, if you didn't hear about, I'm not assuming any prior knowledge to this. We're going to discuss how it's being composed. But if you already knew about it, it's a good revision to you. So the idea is we compose DRAM cells. Remember, our DRAM cell is composed of a transistor and a capacitor, basically, right? So you have a transistor, and you have a capacitor that's basically is used to store your cell, right? Here you have VDD, and here you have your ground. Okay. This is a capacitor, and this is a transistor. And my drawings are bad, I know, but yeah, you have to bear with me because we don't have beautiful slides. So the idea is that this is storing a single bit. How do we store these bits together? In DRAM, we make a 2D array of cells, okay, that we call rows and columns. So there is a 2D matrix here where every single intersection is in fact one cell, right? A transistor and a capacitor. And we call this a DRAM bank. Okay, so this is called the DRAM bank. A bank is composed of multiple rows, so we call these rows. And we call these columns. Okay, as if it's a matrix. Good. Every single intersection of a row and column is storing a single bit. Okay. Great. And then to improve parallelism, what we do is because DRAM latency is in fact very high, we want to optimize for it. So you want to improve parallelism by having multiple banks on a chip. So most of your DRAM DEMs, if you take a DEM, you will find that the DRAM DEM is composed of multiple banks, and every standard tells you how many banks you can support. Like in DDR3, for example, you have 8 banks. In DDR4, you can have up to 16 banks. In DDR5, you can also have 16 banks. Good. So you can have 16 banks in a single rank, as we discuss the concept of ranks now. But the main idea is I combine multiple of these banks together. Such that first of all, I increase the capacity, and also these banks are mostly parallel, so you can access them in parallel. Good. Accesses to the same bank have to be serialized, while accesses to different banks must be run in parallel. Good. And then you take multiple banks and you compose out of them something you call a rank. So you simply have bank here, a bank 8, and out of this number of banks, all of this is called the rank. Okay. Physically, if you have ever seen a DEM, it's called DEM because you have in fact modules in both sides, right? One side of it, you will find 8 chips, and those 8 chips together can constitute a rank. So you have rank 0 on one side and rank 1 on the other side. Good. We'll discuss now why we need ranks and channels, but one philosophy of designing DRAM is you try to have a hierarchy of levels to increase parallelism as much as you can. Good. So we said a cell is just your single bit. You have a matrix of rows and columns of cells that gives you a bank. Multiple banks are combined together to give you a rank. And then in reality, multiple ranks together can be combined. So if you call this a rank, multiple ranks can be combined together to compose what we call a DRAM channel. Okay. So our hierarchy right now looks like a channel that has multiple ranks, rank 0, rank 1, etc. A rank is composed of multiple banks. And then a bank is basically a matrix of rows and columns. Good. Okay. So the terminology DRAM channel, in fact, is a very confusing terminology, both in industry and academia. And the reason is sometimes people say a DRAM channel and they mean different things. The easiest, and I found the most convincing, is you define a channel as something that is completely independent. How do you say it's completely independent? It has its own separate memory controller on the chip. And most modern SoCs, in fact, have more than one memory controller. Good. So if you have one memory controller connected to multiple DRAMs, you don't call these multiple channels, because at the end of the day, they will be bottlenecked at the scheduling at the memory controller. So they're not independent. A DRAM channel is basically a memory controller connected to a DRAM multiple chips, right? Like whether they are multiple ranks, a single rank, a single channel, multiple channel, doesn't really matter, right? As far as you have a separate memory controller for every channel, that's a different channel. This is our definition of a DRAM channel. So a DRAM channel is one memory controller on a chip connected to, well, a DRAM, main memory 0, for example. And then you have another memory controller that connects to main memory 1, etc., etc. By doing this, they are completely independent, right? Independent means on the same cycle, you can serve requests at channel 0 and serve requests at channel 1. If you have one memory controller that is connected to multiple of these channels, which in fact is possible, well, they are independent once they go off chip because they're separate chips. But at the end, they will be serialized here and here. So they're not completely independent. Good? So our definition of a DRAM channel is bare memory controller. one memory controller and associated an off-chip memory, we call this a channel. Good. Yeah, true. Much more parallelism. That's true. Yeah, in your desktops, for example, if you have ever assembled a desktop, you will find multiple slots for your DIMMs. But at the end, you don't really have as many memory controllers on a chip as the number of DIMMs you have, right? So in that case, you might have two memory controllers in most of the advanced Intel chips. So in that case, you will have something like this, right? So one memory controller will be managing more than one DIMM channel, right? You see what I mean? So in that case, there is still some serialization points. They're not completely independent. Yeah.
Is that because memory controllers are expensive?
It's an expensive resource. Exactly. It's one of the most complex blocks in modern computing systems, and we will discuss it in a bit of a detail. So it's expensive, and they say, okay, if our bottleneck is in the data transfer to the off-chip, I can parallelize them, but then I will be serialized at the memory controller. So it's a cost versus performance trade-off. That's true. Good. Okay, in modern SoCs, in fact, where you have like a distributed network and you have multiple chips, so you might have a network on a chip, something like this. This is your interconnect. And then for every router or node, you might have your CPU agents. What they put is, in fact, sometimes they put a memory controller in one place, and the memory controller, sometimes they call it in the far end of the chip, and another memory controller in the far end of the chip. And this allows you to connect to a memory here and a memory here, right? There are multiple memory controllers per chip, and this allows you to connect to independent DRAM channels. Okay? And the reason that they want to have multiple is also to minimize the time it takes from the CPU to traverse to the memory controller on a chip. Okay? So they try to separate them physically on the interconnect as much as you can. Okay? Yeah, that's a good question. In such distributed manner, it doesn't mean that you really partition your memory. You can partition if you would like. You can let this CPU only access this memory, but most of the time you allow every CPU to access any memory. But we have the concept of what we call NUCA, or non-uniform cache access pattern, or non-uniform NUMA, non-uniform memory access pattern, where an access to a memory is faster than access to another memory. You take more time to traverse them. So you want your data to be closer to you. And then there is a whole bunch of research and interest on how to make the data you access more frequently closer in the memory that is close to you, right? And what type of memory you make close versus what type of memory you make. Because these two memories, in fact, in advanced chips can be of different technologies. You can have here like a DDR DRAM, which is what you have mostly in your laptops. But here you might have something like HBM that is more catering GPU access traffic, for example, high bandwidth memory, or GDDR, which is graphical DDR, right? So there are other types of DRAMs that also catering different types of processing elements. Yeah. Physically in the interconnect, like the definition closer in a network on a chip is how many hops you traverse in the interconnect, how many routers you pass by an interconnect. Yeah, to reach to your destination point. Okay. Good. So going back again, I just was showing you this idea of a channel, and we have multiple memory controllers per chip. Going back to the architecture of how really we make accesses to the DRAM. So if I go back to this figure, where we have multiple banks and columns, etc., and we want to access them. So now we do understand that our memory controller is our intelligent brain to handle accesses to the memory. But first of all, what are these accesses to the memory? When do I would have to go and access the main memory? Under what condition? And what we discussed in previous lectures. Are all load store instructions from the CPU goes to the DRAM? Which ones we need to send to the DRAM? Yeah. True. So the ones that miss in all the levels of the cache, right? And we usually call, if you look into this chip, we usually call your last level of cache LLC, last level cache. It can be your L2, it can be your L3, it can be your L4, but simply this is the cache that it's the last cache level before you go to the off-chip memory. Good. We call it LLC, last level cache. So in CPUs, usually accesses to the memory, going to the memory controller, are your last level cache misses, right? So remember, every cache you hit or miss, in every cache level, if you miss in the L1, you have to go to the L2. If you miss to the L2, you have to go to the next level. If you miss in the LLC, you must go to the DRAM. So memory controller or DRAM accesses are usually last level cache misses. Good? Are you good? Okay. So in that case, I want to serve those last level cache misses by sending them to the particular address, to the DRAM cell that has the data of this request, right? So I have a last level cache miss. It's a cache line miss with 64 bytes usually. I want to bring these 64 bytes from the off-chip memory to the last level cache, and then last level cache to the next level, etc., until it reaches to the CPU, right? How do I know this? DRAM simply has no concept of a cache line. It just gets an address, and you need to translate this into what row and column and bank and rank I want to access. This is called address translation. Who does this address translation? It's the memory controller, right? So one block of the memory controller, just to show you the operation, I have a memory controller here, and I have my bank. Now let's focus on a single bank, and then the discussion can be generalized later on. These are your rows, and we call this our row decoder, and we call this column decoder. Well, should be the, is that true? Yeah, column decoder. And then we have something here that we call row buffer in every bank. These are your cells. And the idea is, I get a request from the last level cache. It's a cache miss. This request is an address and a type, right? It's a load or store, and simply read or write, and the address that I want to write from. You take this address, and you have to extract. In the DRAM, you have to send the address in two stages. First of all, you need to determine what is your row. You fetch this row into this row buffer as a whole, and we call this the row decoder stage. So you take the address, extract the row bits, and then send the row bits to the row decoder, and the DRAM will be able to read that whole row into the row buffer. Next stage is you send the column bits to read specific rows from the row buffer and send them on the data bus to receive your 64 bytes at the memory controller. So first step is row decoder, row address. Second step is fetch the row from, we call this row activation. You bring the row from the DRAM cells into the row buffer. Third stage is do the rare read or write from the columns. It's called read or write command. This is the column address. And then finally, you send your data on the data bus from the off-chip memory to your memory controller, which later on it will send really to the LLC. This is your step number 5. You forward your data to LLC. Good. So again, I take the address, extract the row, send to the row decoder of the DRAM. The DRAM will bring the whole row into the row buffer for a reason that we're going to mention now. It's for performance purposes. And then you send in the next stage, you activate this, we call this row activation. You activate the row. And then in the next stage, you send the column address to the column decoder. The column decoder will read particular columns out of that row buffer and send the data to the memory controller that later on will have to send to the LLC. So this is how an access from the LLC to the off-chip DRAM through the memory controller happens, and then the data comes back. Good? Are we good so far? So now we defined stages of accessing to the DRAM. We said, first of all, we said a few things here. We said that the address has to be provided to the DRAM in 2 stages, not a single stage. First, you provide the row address, and then you have to provide the column address. Why do we do this? The main reason we do this is that, again, cost. You want to minimize the DRAM chip cost. One of the highest costs, and this is something we have mentioned when we talk about control path and data path, one of the highest cost elements in any chip, do you remember? What did we say? Is the number of ports, like the number of bins in the chip. If you are in a chip design business, number of bins is really what defines your cost. This is the highest cost element. So if you want to minimize costs, cut down costs, minimize the number of bins. If I were to receive the whole address into one stage to the DRAM, if my address is 32 bits, I need 32 bins. If my address is 64 bits, I need 64 bins. That's too much. So the way DRAM cuts down this is through a clever technique that it takes the address into two stages, into two multiplexer stages. The first one, it receives only the raw bits. And then in the next cycle or the next phase, it receives the column bits. For that reason, you see that in the DRAM chip, you have a smaller number of bins than the number of address bits. Good? Yeah, the column decoder receives the column address, which says for your particular address what particular columns you have to read, and use it to read those columns from the row buffer, send the data to the DRAM. Because the row is a very big chunk. It's like usually 2 kilobytes, 4 kilobytes, but you only need 64 bytes. So you need something to tell you out of this address, I only need these columns, which is the next stage. You will not be reading the whole row, send it to the memory, because this is a lot of data to transfer. No, the column decoder, yeah, well, it's part of the whole circuit. Okay, I see. So if you want, if you want to put this column decoder below the row buffer, and if this is the one that is being attached to the row buffer to read these particular cells, that's also fine, right? This circuitry is not separate. I'm just showing it at the architecture level, right? But again, the column decoder is the one that is picking the particular columns you want to read out of the row buffer.
Like maybe slightly unrelated, but is it possible for your different levels of caches to have different widths
of cache line?
Cache line?
Yes, okay. But it's very complicated. The reason is there are valid bits, there are coherency topics that we didn't discuss. If you start having different cache lines, it complicates your cache controller, because you need to know, now I receive from the DRAM a 64 byte, but I need to know which, for example, if my next level close to the CPU is only 32, which 32 I should send. And then you need to make some decision. If the other cache, there is a topic in the cache that we didn't discuss, I deferred after the DRAM, which is how do we write and read from the DRAM? There's something called write back and write through and that stuff. If the lower level of the cache is updating a cache line, which byte or which bytes of the cache line is being updated? If everything is the same, it's just a clear, easy to maintain, right? So most modern chips, at least the consumer ones, maintain the same cache line across the hierarchy. Okay? Yeah. That's a very good question. Yeah, questions? Good. So what we discussed so far is how do we transfer something from LLC, well, send the request from the LLC to the DRAM through the memory controller and get the data back. And we said, so we discussed first of all sending the address into two stages. And for that reason, the memory controller, one of the blocks of the memory controller is to do address translation, which is simply taking your physical address, 32-bit or 64, and out of this address, this is your 32-bit. Out of this address, you determine, okay, this is my cache line offset. This is my row bits. This is my column bits. This is my bank bits. This is my rank bits. This is my, well, let's say this is the 32. These are my channel bits, right? So it breaks down the address into the low-level segments of the DRAM to route it to the correct bank, correct row, correct column, etc. Good. This is called address translation. Remember, we had a similar address translation needed for the cache. We take the 32-bit of the cache, is we need to determine the offset, the tag, and the index for the cache level, right? So the same exact address traverses the memory hierarchy and it goes through multiple levels of translations, right? And in reality, it's an interesting topic. How do different translations kind of align together? Like if I do my set, where does my set really reside? Is it within the column bits of the DRAM, within the row bits? What is better in terms of performance, etc. Something of code design between different levels gives you good performance. Good. But this is basically, we say you do an address translation from the physical address to the DRAM low-level segments. Okay. Good. But a DRAM memory controller does not only do translation. In reality, we had here a simplified scenario, and this is why I brought up the row buffer issue. Assume after we have done this access and I brought the whole row to the row buffer and I did my reading of these particular columns, the next address, so assume that I had an address sequence, address 0, request 0, it was targeting bank 0, row 0, and column 0. And then I did all this process that we just explained. Then I have another address, another mess afterwards from the LSC that also targets bank 0, row 0, but then column 10. Now, if you think about these steps, you have already brought the whole row to the row buffer. And the row buffer works as a small cache inside the bank. You can think of it as your small cache. So if I already have the row 0 in my row buffer of bank 0, I don't need to really bring it back again because it's already there. So you can cut down your row activation stage and the row address stage, and you jump directly to sending the column address and the particular read-write command to read the specific column, which is column 10 in that case, right? So unlike the first address, which needed an activation, row activation, and then column read or write, this next address didn't need an activation stage at all. It only needed a column read or write. Why that's the case? Because it's targeting the same row that is in the row buffer. Good. We call this a row buffer hit, right? Again, if the row buffer is a small cache inside the bank, hitting into that cache would definitely give you way better performance than needing to do the row activation again, right? The worst, and we'll see this later on from what we call timing constraints, but the worst timing, the delay that the DRAM takes is in fact in activating the row, right? This is your critical path. So minimizing most of the DRAM scheduling we will see in the memory controller, likely after the reading week, is that in fact in minimizing the time, the number of times you need to activate new rows. So it will do a lot of request reordering to make sure that once you bring a row in the row buffer, you keep hitting into the row buffer, maximize the number of hits. Good. So this is a best case scenario because you only need to do one of the stages, not the two stages. So you save a lot of time. To give you some physical numbers, to have some sense of it, a request that would require activation and column read or column write would take something between 20 to 30 cycles. And then cycles can translate into nanoseconds for a 1 gigahertz DRAM, right? A request that would require only a single read or write, we're talking about less than 10 nanoseconds, well, 10 to 15. So it's a 2x difference in performance.
You say 20 to 30, do you mean for just purely that operation, not the...
Both together. Yeah, sorry, you can continue your question, not the data transfer and sending to the...
not the whole process of like in that.
Yeah, true.
20 to 30 just for that portion of it.
Yeah, which is activating the row and start transferring the data on the data bus. That's true. Yeah. Good. While this one is at least 2 to 3x better. Okay. Now, this is a bad scenario. This is a better scenario. In reality, that's not the worst scenario. The worst scenario is, what if I had address 2 that is targeting bank 0, but is targeting row 1 and then column 5. So it's targeting a different row than the row that is existing in the row buffer at the moment. Good. Unlike caches, where you can in fact, okay, I target a different row, I activate that row to the row buffer, and then just ignore the data that exists in the row buffer that is old. You just evict it. Well, you cannot do this. And the reason is, reading from DRAM cells is a destructive process. Why is it a destructive process? Your electronic expertise should come into play now. What are the DRAM cells? Capacitors. Reading from a capacitor is going to, in fact, bleed the data, bleed the charge out of the capacitor, right? So it's a destructive process. So any row fetch or row activation from the DRAM cells into the row buffer makes the data in the row cells themselves obsolete, stale, because the capacitors have been bleed, like they are, that charge has been leaked. Good. So the only location where your data now is valid is in the row buffer, which means before now I need row 1. Before you activate row 1, you have to make sure you wrote back row 0 to the original cells, from the row buffer to the original cells. Make sense? Because otherwise I will lose row 0 data forever, right? This is an operation called row precharge. And again, you can name it from a capacitor. Precharge is because you are precharging the capacitors of these cells. Good? So for this address, you need, in fact, 3 stages, not 2. The first one is a precharge operation of the old row. Then, once you do this, you can activate your new row. This is row 0. Activate row 1 in your access, and then do the read-write access of your columns, basically. Good? So this is the absolute worst-case scenario for any request to the DRAM. You are targeting a data that is different than the data existing in the row buffer. We call this a row conflict. Okay, so if you want to give names into this, and this terminology is very important, we call the first one a row miss. Simply, the row buffer is idle. Assume this is just at the beginning when you boot up your system. The second one is called the row hit. And then the third one we call row conflict. Okay? In a row hit, that's your best case. You only need a read-write command to the column. In a row conflict, that's the worst case. So maybe I should organize them that way. So row hit, best case scenario, you only need a read-write stage. Row miss, which is sometimes people call it row idle because nothing in the row buffer, you need activation plus read-write stage. Activation to bring in the row to the row buffer. Then worst case is row conflict. You guys don't need to write. I will just share all these notes with you. Well, you can still write if you see that I'm not very organized at all, right? And then you just would understand what you write for yourself. But I will just share this one note with you if this saves you any time and then focus. So row conflict, you need to pre-charge plus activate plus read write. Okay. So I will have to stop here and take questions because if this is very fundamental to understand what is after. Yeah. Yeah. So in a case of a row head, you don't send the row address at all. So the memory controller will only be sending the column address, which will go to the column decoder to point to the correct columns in the row buffer here. You mean which ones needs row bits and which ones need column bits? Yeah. When you say row bits, you definitely have to go through the decoder. That's correct. So the first one only needs the column decoder. The second one and the third one, they need the row decoder, definitely. Okay. And then the column decoder. In all cases, you have to do a read-write anyway. So in all cases, you need the column decoder. While you only need the column decoder in case of you have a row head, so you don't need to send the row address. In the last stage, so now the question is how is the last stage different from the second stage? The last stage, before you are even able to send the bits, the row bits of the new row that you want to access to the row decoder, which happens during the activation stage, you need to pre-charge the old row first. Because you realize that I have a different data than the one in the row buffer. And this pre-charge is simply doesn't need an address at all because you're telling a bank, whatever you have in your row buffer at the moment, just write it back to your own DRAM cells. You only need to send the bank address. Good? Because you are not pointing to a particular row at the moment. The pre-charge operation is a bank operation because there is a single row buffer in every bank. Every bank here has a single row buffer. So if I want to do a pre-charge operation, I can just say bank 0, pre-charge your row buffer. It will go to the row buffer, copy the data from the row buffer, put it in the DRAM cells back again. Yeah.
Row buffer, main function of it to avoid recharging, or is there also like locality to it where some rows store information such like address information such a way that they can be dependent, or?
Yeah, in reality, the row buffer. So there is a physical. I mean, just presenting the row buffer as a cache is in fact an architecture abstraction. But I will ignore the physics of the row buffer at the moment. I will come into back later. But let's think it from an architecture perspective. If you have your raw data in the row buffer, you leverage the hits into it. And again, with the locality concept, any accesses that will hit into the row buffer will have better latency. Well, if you assume locality, then it should be very common, right? And in addition to the locality, the memory controller also invests a lot of circuitry to do scheduling to maximize the row hits.
But regardless of locality or not, you still need the row buffer.
Here comes the physics point of view. In reality, the row buffer wasn't done originally to cache for performance purposes. This row buffer in physics is nothing other than sense amplifiers. Did you guys cover amplifiers in electronics courses? Basically, DRAM cells, they don't have enough charge or power to be able to transfer the data into the bins, IOs. So they need amplifiers to amplify the signal. Because one way to minimize the power cost of the DRAM is that this thing is basically VDD is 1.2, sometimes 1.5. Like in DDR4, it's 1.2. So it's a very small charge. By the time you read your capacitor data and put it on the bins, you would have already lost most of your charge data. So one might become zero by the time you transfer it. The way they solve this is they put a bunch of sense amplifiers, one for every column basically, to amplify the data that you read from the capacitor before you send it on the I/O. Good. So the main purpose of, in fact, buffer is just a pure amplification process. But they found that, well, since the sense amplifiers would keep that data unless you overwrite it, then it can work as a cache. Right? Makes sense?
I guess I re-ask the question is it common that going through levels of cache and then you come to the DRAM and you need an address that address and the addresses around it in the row could in like modern day
can hit. Yeah. That's a very excellent question. So and the way you also phrased it is very good, because what Stephen is saying is, I missed in the L1, I missed in the L2, I missed in the LLC. This is not a good locality pattern anyway. So if I go to the DRAM, what locality you are talking about, right? Put in mind that locality is a definition of how large is your block size. Within a cache, if you miss, that means your access is away by more than 64 bytes because your cache line is 64 bytes. A row is in the range of 2 kilobyte to 4 kilobyte. So a row holds multiple cache lines in the same place. So you can still miss in caches, but hit in the row. You see what I mean? Did this answer your question?
Yeah, I think so. So like you can have like 64 byte or 30 bytes on
cache lines that are misses, but then they still keep exactly because one row. So this row buffer thing, it will become crowded now. So one row, if it's, let's say it's 1 kilobyte and your cache line size is 64. So how many would have cache lines here? 6, and this is 10, so it's 4. So you have 16 cache line sizes, right? So a 1 kilobyte row, you would have 16 cache lines. Now, if you access your cache in a cache line granularity, like you access cache line 0 and then cache line 1, this would be a miss. But within a row, cache line 0 and cache line 1 are back to back. So once you access cache line 0, you bring the whole row to the row buffer. Everything goes to the labels of caches. Next access is to cache line 1. It's a miss in L1, miss in the LLC. Goes to the DRAM. Well, cache line 1 exists in the same row. So it's a hit. Good? True. This is why we say there is a lot of scheduling happens in the memory controller to be able to put requests that are targeting the same row back to back. But not only this, it's mainly also dependent before the scheduling on the application pattern itself, right? Because if your application has a very large stride that jumps in a 2 kilobyte, like a matrix multiplication that is row-wise, for example, then you will jump even larger than a row buffer granularity, right? So you start having low conflict. So it's an application, like everything that is managing performance in our discussion. It's an application pattern dependent and hardware capability dependent. Okay?
Would it be possible to get the row miss situation in any other scenario than your system startup?
Good question. Thanks a lot. I like a lot of your questions today. So yes, and this is because of an operation of the DRAM that we didn't bring up at all until the moment what we call DRAM refresh, right?
Because of the charge.
The charge, exactly. So, but I will discuss this in a second. But after a refresh, everything is just as if you boot up. So you will, all your rows will be idle in the banks. Yeah.
Just to confirm, is the memory controller that tells you if you're going to have a row hit or a row miss?
Yeah, that's also, this was going to be my next discussion. Again, a good question, thank you. So the idea is, now, who tracks, now I'm saying for this request, I need to send these stages or commands. First of all, who sends these commands? It's the memory controller. So the memory controller, we started this whole discussion when I said the memory controller does not only do address translation, but it also does other things. These other things are sending these commands to your DRAM chip. So DRAMs are in fact controlled or organized by an industry standard that's called JEDEC standard. This standard basically is a consortium of different industry and academic factors, all of the manufacturers of DRAM and CPUs, etc. They come together, for example, to work on what DDR5 is already on the market, but DDR6 that is coming in 3-4 years, if there is DDR6. Then they are now working on finalizing the standard for DDR6. So they sit together, what are the technology challenges and changes we're going to make from DDR5, how does it work, what are the timing constraints, can we have an early manufacturing chip to study how does it work, and they come up with this standard. This standard defines what? It defines your bins, the chip itself, which is pretty much like it's very natural, but also defines how that you should access the DRAM. So those manufacturers of the CPU that are designing the memory controller will know early on from the standard, if I want to put my DDR5, I don't know, 1600, 2400, whatever you buy as a DDR5, as my main memory on that DEM slot in my desktop, this is how I should operate my memory controller, right? So I should adhere to these timing constraints, which we're going to talk about in a second. You should adhere to this type of commands you need to send. You need to do the address translation in that way. All of this is just defined by the standard, which is a document similar to ISA, but it's a contract between the memory controller manufacturers and the DRAM manufacturers. Good? So now a memory controller will be sending these commands. But to be able to send these commands, you need to track whether this particular address, when you receive from the LLC, whether it's going to be a row hit or a row miss or a row conflict, what commands do I need to send? What does that mean? It means you need to keep track of all the bank states of the DRAM. And you need to keep track of this bank right now has this row address. If you receive another address, you compare. If they match, that means it's a hit. If they don't match, it means it's a conflict. Good? So the memory controller keeps track of all this circuitry, which is the bank state, what rows are currently open, what commands, in what stage your bank is currently in. Is the bank recharged, idle? Is the bank having a data ready in the row buffer? Did you activate a bank, which you brought a whole row, but you didn't do a read write yet, right? And based on this, it sends the correct command. So the memory controller is the one that has to adhere to the standard or satisfy the standard requirements to make sure that you are sending the right commands to the DRAM. Because once you send a wrong command to the DRAM, all of the things, you either have a data corruption or the DRAM will go basically out of sync, right? So all the memory controllers is the one that are maintaining this correctness. And that's why we said the memory controller is the brain of the main memory system, okay? Great, so these commands are being sent by the memory controller. So the story will be, memory controller is receiving an LLC mess with an address and a type. It will take the address, do the address translation. So I receive this address, so it's a miss address. After the address translation, I know exactly my bank, my row, my column, etc. I take the bank, go to my bank state machine, tells me that, yes, this is a row hit, this is a row miss, etc. And then based on this, you send your DRAM commands. Called this command generation process to the DRAM. These commands are either activation, pre-charge, or read or write. Good. Then finally you send it, you send the command through something called command bus to the DRAM, and then you send the address. This bus will go to the DRAM to do the correct operation. Good. Is there any question? So now to complete the story, these commands cannot be in fact sent back to back, because if they are sent back to back, like in one cycle I send an activation, the second cycle I send a read or write, it will not lead to this large delay differences that we're talking about. Like we said, and just again to give you the full sense of numbers, we said the row head is somewhere in 10 to 15 nanosecond. Then a row miss is in the range of, what number did I give? 20 to 30? This one is in the range of 100 nanoseconds, right? So, which means there's an order of magnitude difference in access time between a row miss, a row conflict, and a row hit, right? 10x difference in latency. In reality, this is why I find the naming DRAM is in fact an ironic name. Because do you know what is DRAM? Or what does it stand for? Yeah. True. And what does it mean to be random access? Hmm? Yeah, I mean random, because also SRAM is called static random access memory, but random doesn't mean you access random places. It has a particular meaning. It's related to latency. Random access, when you say a data structure is random access, what does it mean?
Same amount of time for any.
Exactly, same amount of time to access any entry of this data structure, right? So SRAM is random access mostly because in caches, whether you target set 0 or set 1, just it takes the same amount of T-head. But in DRAM, whether I access this address or this address, there's a 10x difference in latency. It's not at all random access, right? So it's a very ironic name, right? It's not in fact satisfying the truth. DRAM is not truly random access, right? There is a 10x difference in performance based on what address you are targeting at the moment. Good. So now, what I was saying is that if these commands are being sent one cycle after the other, you will never have this 10x difference in performance. So they must be spaced out, right? And they are spaced out because these are physical operations you do. Like if I go back to my drawing here, if we take the row activation as a command, as an example, what are you doing here is you're doing a physical circuit operation. Like you are going to a particular, through the row decoder, you are picking up a row, reading all the data from these capacitors, transfer them on the bus to store them in the sense amplifiers, right? This takes time. And this time is something that you can physically measure. And this is what the standard defines. So the standard, the JEDEC standard, defines timing constraints, something called timing constraints, that basically looks into the physics of the operations based on what technology node you are manufacturing this in, how fast your DRAM clock is, and tells you to do a row activation as a memory controller. You must wait after a row activation, you must wait for 20 cycles or 20 nanoseconds or whatever it is to be able to make sure you have a stable row in your row buffer. So it means that the time it takes for this operation to complete before you can do the read and write from the row buffer. Because once you finish the row activation, I can go to the third stage. But if you don't wait for enough time, let's say, for example, I did the row activation and immediately after, didn't wait for enough time, I did my reading or writing. What do you expect to read or write? Garbage, because your data didn't yet arrive safely to the sense amplifiers, right? So every single operation of this is a physical operation that takes physical time. Part of the JEDEC standard committee to come up with these numbers, they have tables. If you open I can put in part of these slides like a data sheet from one of the DDRs, DR3 or DR4. You'll find that there are massive tables that are called timing constraints. It tells you for row activation, which has a particular naming, it's called TRAS, which is the time between activation and reading or writing. You have to wait for 15 nanoseconds if you are running at this speed. And if you are running at this speed, you have to wait for this X nanoseconds, etc. Good. We call this the JEDEC timing constraints. Okay, and the memory controller needs to keep track of the JEDEC timing constraints, because if you don't satisfy the timing constraints, if you send the correct order of commands, but you don't send them within the correct timing, you will not get correct data. So I need to send the right commands, and I need to send them within the correct timing. Good. So to give you an example, assume initially my bank is idle, so there is nothing in the row buffer, and again the memory controller is keeping track of the state of the bank. Then I get a request to that bank. So I only need to activate, right? So I do an activate operation. I say this is activate 0. Then the JDK standard is telling me to wait for some time. It's called TRAS. In some DDR, this might be like 24 cycles until you are able to do your read operation, which is your column read operation. Good. And then after you do your read operation, you will have to transfer the data of these columns on the bus to be able to send to the DRAM bus back to the memory controller. So it also takes some additional constraint here that we call this TRL. TRL is the time from the time you issue your DRAM read command to the time you would expect the data to be on the data bus. Good. And after this time, the data will start transferring on the data bus. And it will take some time in the data bus, and this time is called T-bus. Okay. For example, if you want to transfer 64 bytes, and your data, most of your like DEMs are 64-bit, right? If you have seen this before, our DEMs are 64-bit. That's the DEM standard for DRAM. So if I have a 64-bit data bus, and I want to transfer 64 bytes, how many cycles do I need? Well, this is 8 bytes. So I say 64 over 8, it gives me 8 cycles, right? True? Did you get that? So I have a certain width for my data bus. I want to transfer more than this width, so I chop my data into multiple cycles. Good. The nice thing in DRAM is you take less than 8 cycles. And the reason is our DRAMs are called DDR DRAMs, double data rate DRAMs. I don't know if you covered this concept on 3DQ, for example, or not, but some circuitry, if you want to have a very high speed without increasing the clock frequency, you operate both in the positive and negative edges of the clock. We call this double data rate or double rate. Our DRAMs, for example, it's called DDR4. Why is it called DDR? DDR4, DDR5. Why it's being called like this? In your mobile phones, it's low power, LB DDR4, LB DDR5, because it's double data rate. You send data on the bus, both in the positive edge and the negative edge of the clock. How much does this save you? Instead of 8 cycles, I would take how many cycles? 4, because you also divide by 2 for the double data rate, so you take 4 cycles. See, in almost all the DDR chips, DDR3, DDR4, DDR5, you take 4 cycles to transfer a 64-byte cache line from the DRAM. That's only for the bus transfer time, right? This is basically your T-bus. Good. So again, as a summary, to have the full journey of a request, the memory controller issues an activation, send the row address. The DRAM will take this much time, TRAS, to bring the row into the buffer. Then the memory controller will be able to issue the read at that time to be able to read particular columns by sending the column address. And then the DRAM engine will take the data from the buffer, send it on the IOs. It will take TRL cycles to reach to the IOs. Well, I give you some estimate here. This is usually, if this is 24, we're talking about something like 15 cycles here. And then the DRAM will start transferring on the data bus here. It will arrive at the memory controller. Okay.
Does that mean there's 64 pins on the, like, just dedicated to?
Yeah, there are 64. What you call them DQ. There are 64 DQ bins on the chip dedicated to transfer data. That's true. Yeah. If it's 64-bit DEM, because for example in mobile phones you don't have DEMs, you have discrete chips, and those discrete chips have smaller widths. So some chips are 16-bit, some chips are 32-bit, right? So the change from embedded devices to commodity devices, but all the DEMs, the ones that are really physical, that also exist in our laptops, they are 64-bit. Yeah.
DDR requires separate clock, different clock speeds.
Yeah, the DDR will require different clock than the CPU.
Yeah, so
Because it's a different chip.
Right, but in terms of like,
You mean for the double data rate?
would you require 2 different, like, would it improve, I guess, like overall performance to have 2 separate clocks? Or like more than.
But 2 for which? Like 1 for the DRAM and the other one is 4? Or you mean 2 different for the DRAM itself? I use one for which and one for what? Yeah, so basically DRAM is a clock chip, but it only has a single clock. The command bus and the address bus are single data rate. So they only send, well, this is true up until LPDDR5, a very recent memory that is also making the command and the address double data rate for performance purposes. But basically you can have your bus single data rate, so you transfer only on either positive or negative, or your data bus, which is for all the DRs, in fact, is double data rate, so you send both in the positive and in the negative. Why they are doing this? Because up until recently, the bottleneck is really on the bringing the data to the bus, right? Not in the transferring of the command. And this clock of the DRAM is not the same clock as the CPU chip. Your CPU can be running at 1 gigahertz, 2 gigahertz, 3 gigahertz. Your DDRs are talking about if it's DDR4, so it's 2400, right, megahertz, which is 2.4 gigs, right? DDR3, the most commodity one is 1.6 gig, I believe that's the high speed you can run at. So it's another chip, right? So they can run at different speeds. And it's also the functionality of the memory controller and clock domain crossings and these interesting digital design topics of how you transfer between two different clock domains. Right?
And in your earlier, I guess, like the graph you drew,
Yeah.
they less than sends back to memory controller, but because it costs you to demonstrate hardware instances where the memory controller has more data than it.
Yeah. The memory controller, in fact, a big complexity of the memory controller is something called the memory PHY. I have seen like last year a lot of people going for internships in AMD, etc. They're working on the DDR5. I don't know if did any of you have any internship related to PHYs at all, either at Synopsys or AMD? Because the teams we have at Markham here, both Synopsys and AMD, in fact, manufacture PHYs. I had like few that in fact working on these teams. So basically, what are we discussing right now with the memory controller is in fact the architecture side of things, like scheduling, address translation, sending commands. But associated to the memory controller, something called a DDR5, which is your physical IP that is responsible for these type of things, like clock domain crossings, handling the correct electric domaining and like voltage levels, termination, like analog and mixed signal stuff, right? The idea is, yes, memory controller has to handle clock domain crossings correctly, right? Because you are receiving data at a speed, and then you have to transfer to the LLC at a different speed. So the memory controller, in fact, usually divided into two parts, front end and back end, and these two are working at different speeds. Yeah.
So then does the memory controller have like
Two different clocks. Yeah.
the file itself is buffer that's sent back.
Oh yeah, there are a lot of buffers at the memory controller, and we will discuss this. Yeah. Questions? Okay, so if there are no questions, let's take a break. Maybe for 9 minutes, and then we can start at 1:45.
I have a question on a bit of the semantic geometry. So you were saying earlier that one channel is referring to one memory controller.
One memory controller associated with its DRAM, right? Like a DRAM subsystem, basically, right?
Okay. So you can have multiple memory controllers.
You can have multiple memory controllers on a
channel.
Usually for multiple memory controllers in a channel. No, like every controller with its memory is a channel.
Okay.
So you can have multiple channels and multiple memory controllers in your chip. Like you can have something like I will give you an example. But in this chip, we have something that is called North Bridge and South Bridge. This is an I/O bus transport, and they have a memory controller at the North Bridge. They have a memory controller at the South Bridge. So these are two separate memory controllers that can connect to a separate chip.
Okay, but they're in the same
They're in the same CPU chip, but we call this a channel, and this is a channel.
Okay.
So the way I define a DRAM channel is separate memory controller. The reason I'm doing this is because these two are completely independent, right? right? So they are completely parallel, right? Because there is another architecture that can be memory controller, and you connect it to one
Less. Yeah.
like this is also possible. But now this challenge the operate independently here, but they have to make realize that so they're not completely independent, right? And sometimes people, again, this is why I said it's confusing terminology. Because sometimes people call this challenge. Well, yes, they are physical challenges from the DRAM side, but you only have a single memory controller.
Yeah. Okay. Thank you.
Yeah, I had a question earlier about because at AMD we did like for SoC we had like a very large range of clock speeds.
Okay.
And I was trying to see like where there's a reason for that, and I guess I didn't fully understand it at the time, but like I'm trying to see if that relates to this.
Yeah. You mean different speeds?
Yeah, like,
Yeah. Well, in reality, that's one of the main reasons because DRAM again operates at a different speed than at the CPU. And the memory controller, you would have a lot of clock domain crossing buffers and clock domain crossing logic, etc. Right? But this might not be the only reason. Like for example, if in your SoC you have an interface to DRAM is one example of an off-chip IP, but PCIe is another example, Ethernet is another example, and you will need different clocks for this one as well.
But is there ever cases where like you have different clock speeds between like certain caches or like?
That's a little bit unlikely, but maybe for the last level cache where it can be shared, for example, between a CPU and the GPU, then you can start thinking about them, right? So it depends on which domain you are
Like
in.
in this course, I'm trying to like bridge my like.
Yeah, no, that's great. Yeah. Things start making some sense. Yeah, for sure. Yeah.
I had a question for you.
Sure.
I was wondering, for the pre-charge, is that charging the row that you're going to access?
No.
Or it's
The old-
reloading what was in your buffer back in?
Yeah, reloading what was in your buffer back to the cells, which is the old row.
Okay.
Before you activate the new row.
So it's like you almost borrow that row from where it is in memory, plug it into the buffer, and then you have to return it before you can do anything.
True. What I was saying is this borrowing thing is reading from a capacitor. It's a destructive process. Like once you
Right. Yes.
so it means you lose it from the
To
cell.
be able to access that row,
Yeah.
you need to take the charge from the value.
Exactly. And this is why you need to put it back. And this is why it's called the pre-charge, right? Because you basically charge it back.
Intuitively, I would think recharge because
True.
you
True,
took the charge
true,
away.
true,
Because to me, when I think recharge, I'm thinking
Like charging
I'm
before.
charging the row.
Oh, the new
before I
one.
access
I
it.
see. Yeah, I don't know. That's well, a good point.
So it's charging the old row
The
that
old
you
row.
just finished
The old row.
access.
Yeah.
Okay. Okay. And then I didn't get to copy down some of the stuff that you said you're gonna post.
Yeah. This thing was good.
Okay. Thank you.
Thanks.
Size of being older than the hard drive to reduce the price of the machine. Like what was that?
The size of
The bin.
Oh yes. What I was saying is that if you look into a DRAM chip, you need some address and some data, right? Now, if you make your address space equal to your address width, which is 32-bit, for example, right? You need 32 bits. But that's too much. And DRAM want to minimize that. What they do is instead of having like 32 bits, they give you something like 15 bits. And they tell you, send me this 30 or 32 or whatever into two stages. I read first the first 15, and in next stage I read the second 15. You see what I mean? So it takes a multi-cycle operation because you minimize the number of additions.
How about the data?
Well, data is not multiplexing. Data is just you have to transfer the data all in one. So the data, if you are transferring, if you have a 64-bit request, 64-bit. If you have a 16-bit, it's 16-bit. So this is not multiplexing. This is
That is in order to reduce the price or reduce the size of it.
exactly. Yeah, both. Because both are function of each other. Reducing the size, reducing the number of bits would reduce the area of the chip, which will reduce the price. Well, this decreases efficiency. Yeah, because like having it in two different phases, you basically have to do the act first. And then after some time you do the read write. Here you send the row address, and here you send the column address. So it takes a lot of time to do the two phases operation. If it was a single phase operation, it would have been faster.
question about the column decoder.
Yeah.
Is it getting 1 bit or a full cache line?
Oh yeah, that's a good question that we didn't discuss yet. So in reality, there is something called column width, which is multiple. A column is not constituting a single bit; it's multiple bits, and this is also part of the data sheet of the DRAM you buy. When you say it's a by 8 device, it means that your column is 8 bits. So a single column is 8 bits. From where did you get your 64 bytes? It's something we're going to explain. Okay.
Okay. So I'm assuming that like you iterate your column and then get.
That's one thing you
one
do.
way you could do.
But that, well, in fact, you do that, which is part of the operation. But you also read from multiple chips in parallel to be able to get the whole thing.
Okay. Because I was so confused when you were saying you get 64.
Yeah, no, sure. I was abstracting but that's a good question. Yeah. Yeah.
Are we gonna cover fuse at all in this? Like fuse?
Oh no.
No. Okay.
Yeah. Well, I know that this is a type of memory.
I don't really understand it, but
Yeah.
we had it, and
Yeah, because it's a not
change your
commodity. Yeah. It's a type of non-volatile memory that is trying to. Well, DRAM has its own limitations at the moment,
Sure.
and it's why people are looking for alternatives. And fused memory is one of them. Yeah. Was this part of your internship dealing with fused memory? Okay.
So we did like,
Yeah.
because like Arjun and I were on the like CF control.
Okay.
Control tower.
Yeah.
And we had like fuse IP.
Ah,
Some
okay.
IPs, some like fuse, but fuse was like in every IP.
I see.
It was
Yeah.
like,
Yeah.
it's like So I guess it's just another type of memory.
Well, it depends really because okay, now we are talking about it might exist in different IPs. The word fuse, there is something called fuse memory, but also sometimes people refer to the fuse as a small block, especially if we're talking about machine learning acceleration IPs. It's fuse multiply add, right? Like you do fuse multiply add. Like most of your convolution process is in fact doing multiplication and then addition, and they call this a fused operation, right?
I think it was memory.
Yeah, if it's memory, then it's fused memory. Yeah, for sure. Yeah. Okay. Okay. So as I said, like at the beginning of this lecture, I'm going to share this OneNote with you. I'm also going to share the last year's slides anyway. My only problem with them is that they keep hopping between different topics. Because I guess I kind of reused slides from different places and they're not very organized. So I will share the slides with you. You will find it's just the same material, but not in the same organization flow that we went through here, right? So you'll have both available to you. So to continue what we were discussing before the break, we discussed the commands you have to send and the timing constraints for a request that was a raw miss, which means your bank was idle, maybe at the very beginning. You send an activate command, which is this one. After some time, you send a read, and after some time, you extract the data on the bus. Now, what about the other two types, right? What if you are a row head, and what if you are a row conflict? Good. If you are a row head, let's say the second request after this request 0, you have a request 1, and again, let's say this was for bank 0, row 0, then column 1. This is bank 0, row 0, and then column 10. So it's the same bank and the same row. So this is called a row head, right? If it's a row head, well, and let's say it arrives sometime after your transfer of the data, simply you need to only send your column address with a read or write command, right? So you send a read command, assume it's a read, and to get the data on the data bus, right? So for our numbers, this is 15, this is 4 as we discussed. So you take a total of 19 cycles. While for this one, you have taken 24 plus 15 plus 9. plus 4, right? This is from where, I just want to show you on a timing diagram from where the extra time comes for the row mess, right? It comes from the time between the activation and the read. While for a row hit, you don't need an activation process at all because your row is already on the row buffer, then you just issue a read directly. Now, for our third request, assume after some other time, you also access bank 0, but then you access a different row 1, and then I don't know, column 5, it doesn't matter the column at the moment. This is request 1, and this is request 2. In that case, memory control will receive the address, going back to our circuitry here. I do the address translation. I look into my bank state. I realize that the current open row of that bank is row 0, and I want to access row 1. So it's a row conflict. What do I do as a memory controller? I need first to pre-charge the old row. I need to issue a pre-charge command. Wait for some time just to make sure that the data is written, the old data is written to the original cells. Then issue an act command, and then do my read write. This is called the TRB constraint, and usually it's equal to, again, the TR series is like 15 cycles, and then you suffer the usual TRAS of 24, and then you, after TRL, you will get your data. Good. So now for a row conflict, I didn't only add the activation problem or phase, but I also added the pre-charging phase. And this is from where the extra time come into play. Yeah, that's a good question. Different banks have different row buffers. So the concept of a row hit or a mess applies to a particular bank. This is why here we said these 3 requests are targeting bank 0. If this, realize this when you do the address translation, it's comparing the state of that bank. So every bank has its own state. Okay, so every bank has its own row buffer, and this is why accesses to different banks can be parallelized, because they maintain different row buffers. Exactly, you interleave the memory reads and writes across banks. And also memory control scheduling spends enough time and investment into how you parallelize your memory as much as you can. Okay.
Technically, if went to bank 1 with row 1, wouldn't have to recharge because you could leave the row 0 from bank 0 in the buffer.
True. 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 Any question in that? So again, we saw the 3 types, but in a timing diagram. Good. Okay. Are we good? Great. So given we're discussing this, and also urgent question, it might be good to also see what would happen from a timing perspective if you target a different bank, right? So if you go to a different bank, well, there are different set of timing constraints, and because you maintain a separate row buffer, then simply you can also parallelize things. For example, assume you have 2 different row misses, but every one to a different bank. So I have my first request is for bank 0, row 0, and then column 0. My request 1 is in bank 1, and then row 0 or row 1, it doesn't really matter at the moment, and column 0. Okay, column 1 just in order not, or 10 in order. I don't want you to interpret that there's a relationship between the columns, right? Because think about it, once you have a different bank, it's just a completely different column, right? The index is just the same, but they are pointing to different physical places, right? But how would the timing look like, right? If these 2 requests were to the same bank, they must be serialized because you have to wait until the first one finishes, closes row 0 before you open row 1. But if they are two different banks, I can in fact interleave them, used by applying, right? So the way this works is, for the first one, you would have to activate, wait for your particular time to do the read. Then after some time, I start receiving the data. For the second request, well, someone can imagine I can send the act immediately here. But that's not true because they still share the command bus, right? So remember, this is why I said having 2 separate channels is the only true 100% parallelism in DRAM, because you have a separate command bus, data bus, different DRAM, different memory controller, so everything can be parallelized 100%. So you still share the command bus. So DRAM standard puts some smaller constraint into acts to different banks. It's called TRRD. And to give you some numbers, TRRD is in the range. You don't need to know all these names, right? I just know them because I worked with them for a long time. But just to give you some tangible sense, right? TRRD is, I don't know, 4 cycles to 6 cycles, something minimal, right? So there is parallelism, but not 100% true parallelism. And then this is activate to bank 0, this is activate to bank 1. Then after you suffer the timing constraint of the activate to read, you can also issue your read here. Again, 2 different reads to different banks. You suffer also a small timing constraint that we call TCCD. This is governing back-to-back read commands. Why do we have this constraint? Because at the end, different banks on the same channel share the data bus. You must wait until your data is transferred before you finish sending your second data, right? So TCCD, part of it is making sure that whatever old cast command has already finished transferring its data. So if you do this, most likely you will see the data back to back. Okay. Yeah.
The memory controller also have to take into account, like, let's say the first one is a miss, but the second one is a hit. And like the order in which the data comes in could be flipped.
Yeah, true. Okay, that's a good question. So in reality, and we can have this example in fact drawn. Yes, they can be flipped. There is no ordering maintenance in the memory controller between requests to different addresses, because a major aspect to the memory controller is in fact do this reorder, because you want to maximize performance. You do out of order scheduling a lot, right? Unless they are targeting the same address. But if you target the same address and you are consecutive reads and writes, you just maintain the order, but naturally you're not saving anything by reordering them because they are just targeting the same row, which might be idle or closed or open, right? So accesses to different banks, they are different addresses, and hence if you can reorder them to maximize performance, you would do so. Like in this example, assume that the second request was only a row hit, not a row miss. In that case, I'm able to issue my read here. In reality, I can issue my read directly 1 cycle after the act. Between act of a bank and read to another bank, there is no timing constraint. So they can be directly 1 cycle after the other. And then after some time, which is my TRL, I can start receiving my data here. This is just completely fine, right? Just to continue, we can call this request 2 to bank 2. The row doesn't matter, it's a row head. And then, well, 10, 10. And this is a row head. And let's call this 2. And this is a valid sequence in DRAM. Good. The first access to bank 0 is a row mess. The second one to bank 1 is a row mess. The third one to bank 2 is a row head. Good. And it finishes out of order. Okay.
By the that, like, if you got a system that's dual channel but 4 stick memory, there's 2 ranks per channel. So if you switch ranks, you're still limited the same way you are with the bank.
Yeah, no, it's a less timing constraint. So the parallelism in DRAM is accesses to the same bank are more or less serialized. You cannot overlap much. Accesses to different banks, but same rank, we can say parallelism as just 1 check mark. Different ranks in same channel, you can say 2 check marks. Better parallelism, less timing constraints. And then different channels, this is just true parallelism, right? This is everything on the same cycle, you can issue multiple commands. Good. So to have one example, like let's say this sequence itself, between the first one and the second one, both are row misses, but they are targeting different ranks. So it's rank 0, bank 0, and then the row doesn't matter, row 0, column 0, and then rank 1, bank, again, the bank doesn't matter. So you'll have something like this, act, and then your read. This one can be directly 1 cycle after. because between acts to different ranks, there is no timing constraint. And then between reads to different ranks, there is a timing constraint again because of the data bus. Again, ranks still, what makes ranks not completely parallel is they still share the same data bus, the same physical bus of the DRAM, right? A data bus and a command bus is an artifact of the channel. If you have multiple ranks within a channel, at the end, they are serialized on the buses, right? Physical bins, true. Well, a rank is in fact a logical terminology more than a physical terminology. Like the bins are buried channel, right? Right. So think about your DEM, right? You had your both sides. If you think of each side as a rank 0 and rank 1, at the end, your DEM bins are just common between the two sides. Yeah, well, this is. Well, okay. So you are talking about this. These are not ranks, right? These are DEMs within a channel, and this goes back to what I was saying, that people are confused about defining channels. So in reality, what you're talking about is something like this: DEM 0 and DEM 1, right? So these ones here, they have their own separate bins. That's true, but they are serialized at the memory controller, right? These ones, the memory controller can consider them channels, and they don't have, these are not ranks. You don't adhere to the timing constraints there, right? So they can send simply commands back to back, right? But at the end, you'll be serialized into your data bus here. So you cannot really send the data in parallel. Like even if you can send it in parallel here, it has to be serialized here, unless you really double your interface, right? You make here your two separate data buses, one for each channel, right? Which you don't do, right? Yeah, this is a slightly advanced discussion. Yeah.
Could you go back and explain TRD, or I can't remember which one it is.
Yeah.
TCCD.
Yeah. TCCD, for example. Once I send, as a memory controller, once I send my read command, I should expect the data after some time. And the data will take what we said T bus 4 cycles to be transferred on the bus, right? Again, DRAM does not maintain any state, or I should send the data now, or I don't send the data now. I receive a command, I act immediately, right? So if you send your second read command directly after here, the DRAM will go read and push the data in the data bus. So these two data will conflict each other. So you have a garbage. So it's the memory controller responsibility to make sure you satisfy the constraints such that data don't collapse, right? Okay. And TCCD is basing out the caches, what we call these caches or column commands, such that the data does not really collide on the data bus. Okay. So now there is one interesting question to answer, and I guess we can conclude the lecture with that one. And then next lecture we can talk about the specific scheduling details of the memory controller. In the lab, you will have a lot of fun doing a lot of scheduling, read-write scheduling, and first come first serve scheduling, first read, first come first scheduling. That's lab 4. But one question that you should ask is, I told you that there are cells of rows and columns, matrices of arrays of basically of banks. And then I said we need to fetch 64 byte. You, like a last level cache, send you an address is expecting 64 bytes, but your interface is only 64 bit. From where I would get the 64 bytes? From where I get this parallelism? If I'm only going to a single column, I'm reading a single bit, right? What would happen, right? How do I combine these 64 bytes, right? So the idea is there are two techniques in DRAM that gives you larger data than what a single cell is holding. The first one is you combine multiple chips to form a wider interface. Again, if you look into a physical DEM, you will find that there are 8 chips in one side, 8 of them, right? These 8 chips together, everyone has its own data bus width, and they are combined together, concatenated, to give you a wider bus. So if we say our DEM is 64 bit, In reality, that's because it's combining 8 parallel chips. Every one has an 8-bit interface. So 8 multiplied by 8 gives you 64-bit. Good. Now, okay, good. I agree with you that you can give me 8 bytes, which is 64-bit, but I still need 64 bytes. From where can I get this? Using a single address. And here comes the second concept of DRAM, which is called prefetching. So DRAM as a device now, you send one command into it, it gives you multiple data. So it doesn't read a single column, it reads subsequent columns, right? And this is called the prefetch length or burst mode of the DRAM. Good. So I send one address. Think of these 8 chips together. One address will enable all the chip select of all these chips. And it will go to particular column, right? And a column, because of what we call a column width, which is the chip width, is going to give you 8 bits each. Not a single cell, but 8 cells together, right? But not only this, is based on the burst length of the device, which is, for example, in DDR3 and DDR4 is burst length of 8. It doesn't read a single column. It reads subsequent 8 columns back to back. Okay. Why 8? Because burst length of 8 with a 64-bit or 8-byte interface, you can get the 64-byte of the cache line. Good. So I send a single address. I activate 8 chips. I get here 8 bits at a time. And I repeat this process 8 times, which is my burst length. So first of all, I read this first 8 bits from all of them. Then in next stage, I read the second 8 bits from all of them. And this is basically being repeated 8 times. Good. DR5, for example, some of the changes they have done over DR4 is that they have an option of burst length of 16, which means, in fact, I do prefetching of 16 times with this access, right? Well, they added burst length 16, but they reduced the data bus width from 64-bit to 32-bit. So they still give you 64 bytes, but because they reduced the data bus width for power reasons. Good. So the burst length or the prefetch length is basically it's a prefetching technique of the DRAM devices to give you more data using a single access. If you didn't have a prefetch burst length, what you would do? You basically have to send 8 different cache commands to be able to get your 64-byte, right? Because every single cache will give you 64-bit, which is 8 bytes. I need 8 of them. But to save this communication and timing constraint and problems with the memory controller, you send me a single command. I send you 64-byte at a time. Why is designed that way? Because most of the modern systems, they have their own cache line to be 64-byte, right? So they help you to make the common case fast.
Does this imply that the instruction is split up between the 8 DIMMs?
Well, these are not 8 DIMMs. These are the chips on the DIMM. So this is the DIMM.
Yeah, sorry, like, there's one instruction split up between the 8 locations.
Yeah. A cache line is split. In reality, a single address activates all these chips together because simply a chip gives you only 8-bit, and you want to mimic the scenario that, in fact, I'm operating like from a memory controller aspect. You don't have a way to separately activate the chips. All these chips, you look into them as one entity. So the memory controller sees this black box. It doesn't see the small chips inside, right?
Is it costly though to store, like, first split up that instruction to the 8 locations, store it, and then
you have to do 8 different accesses, right? Which is definitely costly, right? And not needed as well. Because
you save costs on that because reading them in parallel is like storing them in one.
yeah, true. Well, but if you store them in one chip, here we're noting this is a chip, it's not a bank, right?
Yeah.
So it's a chip. In reality, every one of these chips has 8 banks, right? So if you store your whole 64-bit in a single chip, what is the cost of this? The cost is the chip data bus is only 8 bits. So you will be able to get 1 byte every cycle. But this doesn't work for you, right?
64 first time to 64 and that.
Exactly, which is too bad, right? Okay, you have to wait in reality for instead of 4 cycles, you have to wait for 16 cycles, right? So it's not good, right? Yeah. So DRAM again to maximize bandwidth at a low cost, it makes the data bus large width, 64-bit, right? And in this case, it is able to transfer to you every clock 16 byte because 64-bit is 8 bytes, and you do this in positive and negative edge, so you get 16 bytes every cycle, right? Then on top of that, you take 4 cycles from a burst length to transfer 64 bytes. This is why I told you here that the T bus is in fact 4, right? If you go back here, we said that the T bus is usually, where did I write this? Yeah, here. T bus is usually 4. Why is 4? Just think about it. Every cycle I transfer 16 bytes. I need 64 bytes. So you need 4 cycles. Good? Yeah?
So is it just like they pick 8 shifts to be the amount of, why not the 2 shifts? That'd be faster.
Yeah, it will not be fast enough because again, if you have 2 chips, like 2 of these chips.
32 chips.
Oh yes. Okay. That's in fact that's a good question. Why in fact I don't have even further wider, right? Yeah. Well, if you have it wider, you make it this 128-bit bus, right? Which means your number of bins now double, so your cost would double, right? Right?
But make each chip instead of 8 bits.
True, but the number of bins is in fact a very sensitive, right? That's really what's critical. And just to, in order not to really dismiss your idea completely, there are 2 different standards that are really adopting the similar idea. First one is HBM, high bandwidth memory. It gets a 1024-bit bus width. So it's a massively parallel thing to cater on GPUs. And the second one is the standard, but it's not very successful. HBM is a successful one. The other one is called wide I/O memory, where they also define a very wide bus. Data bus DRAM, right? But the HBM is the most common used at the moment, so I guess you can reason more about it, right? Yeah.
So how is this byte addressable? Like, how does it know that like it's split across these different cells like that?
Well, when you say how does it know, this is referring to whom?
Like the memory, how does like the program know that the memory is split across?
The program doesn't need to know anything about what we're talking about, right? You only have load store instructions with addresses, assuming a uniform, one big chunk of memory that is just byte addressable. What caches you have, how your DRAM is being composed, that's completely oblivious to you, right? And this is the beauty of making the hardware do all the job in the background, while the application doesn't need to know. When you write your programs, you don't even know this, right? But you can still safely write programs, right? So you don't know. And in fact, even the memory controller doesn't need to know how many chips you have internally, etc. It's the DRAM that receives the command from you and basically returns to you the data that you're asking for. Okay? Yeah, it's a JEDEC specification. That's true. Yeah. True. In reality, up until DDR2, it was burst length of 4. DDR3, 8 came into standard. In DDR5, they are trying to push for 16. Yeah. So it's every protocol generation, every standard has its own burst length. In HBM, high bandwidth memory, which is also a JEDEC controlled standard, they have burst length of 2 and 4 and 8. Yeah, what I was saying, burst length is simply how many times I transfer on the bus, right? True. So if you have a burst length of 8 and you have an 8-byte bus, which is 64-bit, you basically get your 64 bytes. Okay. Burst length of 4. Okay. And you still have your 8-byte interface, which is 64-bit, right? In that case, how many cycles do you need to transfer to 64-byte? How many times you need to transfer? Forget about the number of cycles. How many times do I need to transfer? Well, a single command will give you 4 multiplied by 8, so it will give you 32 byte. Correct? Which means we call this the granularity of the DRAM. Like a single access to the DRAM gives you how much data, right? Now the granularity of the DRAM is less than a cache line, which means the memory controller will be forced to send 2 read commands to be able to get 2 chunks of 32 bytes to combine them to have a cache line of 64 bytes. Basically, how much data a single command gives you is a multiplication of the burst length and the bus and the bus width interface. Bus width, the width of the bus, of the data bus, right?
So would you say that higher burst length is more performant?
Yeah, definitely.
But is that not dependent on the size of your, like your read byte versus?
Oh, and burst length is not dependent on your bus interface, but both together determine your memory access granularity, right? And this is why I was saying burst length of 4 and 64-bit bus interface gives you 32 bytes for a single read command, while 8 and 8 gives you 64 bytes for a single read command. And what is your bus? What is your bus interface? Yeah, exactly. Exactly. Because otherwise you'll be getting 128 bytes, which you don't need. So in that case, you operate on 32-bit bus, and then you get 64 bytes. Yeah. Good. Like I'll give you one practical example. In HBM, the bus interface is 1024 bits, which is basically 1 kilobit, right? Okay, 1 kilobit is, if you divide by 8, that's 1/20th bytes, right? Now, with a burst length of 2, you get 256 bytes. With a burst length of 4, you get 512 bytes. Why these numbers are large? Because HBM was mainly for GPU use case, and the last level cache of GPUs operates on these cache line sizes. Okay? So this data is useful for GPUs. Hooking up an HBM with the current burst length and width to a CPU is a waste of energy and bus width. Good? Okay. Is that clear? Now, how do we get this 64 byte from like the concept of chips and then burst length or prefetch concept in DRAM? Okay. By doing this, we finished almost all the operation of the internal DRAM, how does it really operate, receiving commands, sending data, and also how the memory controller operates in a functionality perspective. It remains to discuss the performance optimizations and scheduling of the memory controller to maximize basically your raw heads, right? Maximize performance. And this we're going to do in 2 weeks, okay? Because happy reading week, all the best for your midterms, and see you in 2 weeks.
Small question.
Yeah.
So you were talking about how DDR5 has 16 bit